Voltage, lesson 5. Let's start with a bit of review. Oh, and again, we're in our wonderful graphics world where that there is supposed to be microcoulombs. I will fix it eventually. It's on my list of things to do, but I'm not looking forward to it. Part A says, okay, so we have a 2 microcoulomb charge, and we're at a field point 75 centimeters away. Part A says, find the electric field, magnitude and direction, 75 centimeters east or to the right of a 2 microcoulomb charge. Okay. Electric field, well, there's 2 ways to calculate electric field. One is if I know the force at a location and the charge at a location. I think they've given me a field point. I don't know the charge at that location, so I'm going to use the point charge equation, the planetary charge, KQ over R squared. It's going to be 9 times 10 to the 9th. It's going to be 2 times 10 to the negative 6 divided by, careful, 75 centimeters, so 0.75 squared. How big is the electric field at that particular location? $32,000, I think, yes? Units? 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 Yeah, comes out of the definition. Newtons per Coulomb. Direction. Which way would a positive charge right there want to move if it could? Right or left? Or you could say east, since the question did mention east. I don't care. What that means is that every single Coulomb of charge at that location would experience 32,000 newtons of force. In fact, part B asks, find the force on a 1 Coulomb charge placed at that point. Don't write this down. Don't write this down. Do not write this down. I could go like this. And that would get me there just fine. But I think I can use this to redefine my equation for force. How would I get the force, the F, by itself from that equation that I circled up there? More specific, F equals what? Instead of writing out the point charge equation, since I already know the electric field at that location, and they just told me the size of the charge at that location, as a shortcut, I could go like this. Right? And since the charge is 1 Coulomb, and I already know that the electric field is 32,000, I bet even Brett can do this in his head. Yeah. What's the answer? 32,000 units?
Well, I had to make sure.
Units? Newtons. Direction, well, we just put a positive charge right there, so it would also experience a force to the right. Cross out C. D. If I wanted to find the force on a 2 millicoulomb charge at that point, again, I could use the same trick. I could say the force is going to be the electric field times the charge. By the way, you can write EQ. I usually write QE for some reason. It's going to be 2 millicoulombs times 32,000, which I think is going to give you 64 newtons. 64 newtons? Okay. So really, Rob, I sort of have two ways to calculate force. You give me two charges, F equals K, big Q, little q over r squared. As a shortcut, if I already know the electric field at that location, all I need is how big is the charge at that location, QE. And they really flow out of each other. So, electric field tells us the number of newtons of force per Coulomb at that location. For energy, there is an analogous concept, a similar concept, that says instead of how many newtons of force per Coulomb at that location, how many joules of energy per Coulomb at that location. And we give this a name. The number of joules of energy per Coulomb at that location is commonly, unfortunately, called potential. Did I say potential energy gradient? Say no. Do kids get potential and potential energy mixed up? Yes. I prefer the term voltage. It's measured in volts. I prefer that term. I understand why the term potential is sometimes preferred because it is more descriptive, it is clearer. Potential implies that you have the ability to do work for something. I think, though, it also just leads to confusion. Oh, and since potential voltage is defined as joules of energy per Coulomb, that means the units are joules per Coulomb, which is the definition of a volt. 1 volt is 1 joule per Coulomb. And then I wrote, we must be careful not to confuse potential with potential energy. We must be careful not to confuse potential, which is in joules per Coulomb or volts, with potential energy, which is in joules. We must be really, really, really careful. We must turn the page. Or next page over. So here is the definition. What's a volt? A volt is defined as how much potential energy per Coulomb there is at that location. That's its definition, and from that definition, we can generate an equation. Example 2 says, fill in the proof to find the potential or voltage due to point charge Q. Potential energy is K Q1 little q over R. Let's go K big Q little q over R instead of Q1, Q2. Voltage is how much energy per charge. What you really have is this, K big Q, little q over R, energy per charge. And it turns out what happens here is the little q's cancel. You want the equation for voltage? The equation for voltage is K big Q over R. That, Courtney, is if you know the size of the great big planet and you're a certain distance away from the planet and you want to know how much voltage there is, how much energy per Coulomb there is at that location. It's K times the charge on the planet divided by how far away you are from the planet. Can get a little confusing. Voltage, also called potential, KQ over R. That's potential. Potential energy, K Q1 Q2 over R. Electric field, also beginning with an E, KQ over R squared. Force, K Q1 Q2 over R squared. Forces and fields, the first row, these are vectors, forget the signs. We decide the direction. In energy, we plug in positives and negatives. And Rob, because voltage is defined as how much energy per charge, We also include positive and negative signs for voltage. Include your positive and negative signs for voltage. For scalars, and voltage is a scalar, include the signs, please. So we have now done every single equation, this one, this one, this one, this one, this one, this one, except this one here. We'll spend a few days looking at this one. We haven't quite done this one. I defined voltage as energy per Coulomb. I think it's reasonable, though, Zach, then to say, oh, I guess the change in voltage would be the change in energy per Coulomb, because it'd be a final minus initial little song and dance. Fine. Is there room to get these confused, Joe? So don't. I haven't yet figured out a way yet to help it not happen. I'm working on it because it drives me crazy. Let's start using this. Let's start applying this. Turn the page. Example 3. Same picture as example 1. Same situation. We have a positive 2 microcoulomb charge, and we're at a field point 75 centimeters east or to the right of the microcoulomb charge. A says, find the potential, the voltage, 75 centimeters east of that charge. Okay. Now, you're going to start to notice a certain habit I picked up from one of my physics profs in college. Later on, in fact, later on today and definitely in the next class, we're going to have an equation that has this and this in it, where one is voltage and one is speed or velocity. My lowercase v's and my uppercase v's don't look very different, and so my college prof, to distinguish a capital V voltage, always put little wings like that to make it look like a type font. I picked up that habit, so I'm going to do this because I feel just weird not doing it. Don't freak out. When you look at my answer keys, you'll notice on most of my capital V's, you'll see little wings on it because I'm thinking I want to distinguish that that's voltage, not velocity. We're running out of letters, which is kind of neat. You've learned lots of physics, but we need a bigger alphabet. K, good old 9 times 10 to the 9th. Big Q, the planetary charge, positive 2 times 10 to the negative 6 microcoulombs, divided by 0.75, not squared. What's the voltage at that location? So not the electric field. How much energy per Coulomb is there at that location? Sorry?
24,000.
24,000? Yeah? Anyone else? 24,000 what? It's joules per Coulomb, which we have given a name. We've called that a volt. Lowercase v. Dylan, what does B want me to find? So not the potential, but the potential energy. Not the potential voltage, but the potential energy. Put your pencils down for 1 second. I could do this. Don't write this down. Where R is 0.75, where Q1 is the positive 2 microcoulomb charge, and where Q2 is the 1 Coulomb charge, except I gave you a second definition for voltage. I also told you that voltage was equal to potential energy per Coulomb. Can you rewrite that and give me a new definition for potential energy? Yeah. I'm going to go QV again. Write that down. And Chen, the reason I can do that is I already found the voltage there. Now, if I hadn't found the voltage there, I would plunge straight into last day's lesson, potential energy. But since I got the voltage there, I think I can just go like this. The new charge that we've introduced at that location, which part B says is exactly 1 Coulomb, very nice, The voltage at that location, U-Chen, is 24,000. In your head, U-Chen, what is 1 times 24,000? You got that right. I'm so proud of you. 24,000 what? Now it's energy. Joules. Mr. Dewick, I got 24,000 volts and 24,000 joules. Does that mean joules and volts are the same? No, it's just because the charge was exactly 1 Coulomb that your magnitude happened to be the same. Let's skip C again, but let's do D. What if the charge was a bit different and I want to find how much potential energy a 2 millicoulomb charge had at that location? So the voltage at that location is still 24,000, but I'm putting a 2 times 10 to the negative 3 Coulomb charge, a 2 millicoulomb charge. Double check me, but I think you're going to get exactly 48 joules, I think. Yeah. So a small charge wouldn't have that much energy. I've been trying very hard to give you a gravity analogy each lesson. What's the gravity analogy for voltage? There isn't really a great one. It's sort of like height. So if I take this golf ball and I raise it up higher, does it have more potential energy? Can it do more work? Yeah, but you know what? It's not really height. It's really height per kilogram. It's how much height per kilogram I have there, because voltage is how much potential energy per Coulomb. So this is where my gravity analogies really start to break down. But you can think of next unit when we look at an electric circuit, a battery. What a battery does is it has a potential difference between the positive and the negative terminals. They're at different heights. Leaving the positive terminal is like me dropping a ball from a very, very high height, except instead of falling, the only way the charges can fall is to go through the circuit. And as they fall through the circuit bleeds the potential energy from them instead of gravity bleeding the potential energy from them. And when they get back down to the bottom of the battery, they're back on the ground at height 0. That's what a circuit is. And so that's where voltage, in fact, when we get to circuits, Zach, we will treat voltage temporarily almost exactly like a height. We'll treat a battery, as a matter of fact, like a chairlift on a ski hill. And we'll set up all of our circuits like ski runs. And if you do that, it becomes very intuitive. Next unit. So voltage, Sam, sort of like how high something is, but it's really how high something is divided by how heavy the object is at that location, because if it's heavier, it can do more damage. Sorta. Kinda. I wrote, if we know the change in voltage, or potential difference. Now, what's potential? Don't say energy. What's potential? What have we just learned about 10 minutes ago? And what does the word difference mean mathematically? Which mathematical operation is implied when I say, so potential difference is a fancy way for saying subtract them. Hey, that sounds like a change in final minus initial, but they're going to call it a potential difference. We're dealing with some archaic old vocabulary here because a lot of the vocabulary was invented before we actually understood what was going on in electricity. If we know the potential difference, the change in voltage between two locations, then I can figure out how much work it takes to move between 2 points. Say what? Like example 4. Example 4. So what I have in example 4 is kind of a diamond shape here. I have 2 charges, both identical conveniently. Both of those charges then would be sending out an electric field, which means that if you put a charge at any one location, it would feel a force, it would start to move, which means, Rob, it must have potential energy. It would either be repelled or fall toward, but it must have potential energy, which means that if I want to physically, on my own, move it around, I must do work. With me so far? one way to find the amount of work done would be to find all of the potential energy at location Y, to go K, Q1, Q2 over R at location Y. Then go K, Q1, Q2 over R at location X, and then go work is change in potential plus J. There's a better way. What does part A want me to find, Vlad? Did they say potential energy, or did they just say potential? Okay. I'm going to call this charge 1, and I'm going to call this charge 2. And I already know from prior experience I'm going to need a fair bit of room. I'm going to do charge part A right up there. What I'm going to do is I'm going to find the voltage from charge 1 at location X. Is that a good way to write that? V1, X? And I'm going to use my KQ over R, Q1 over R1, or Rx, I guess I should call that. It's going to be 9 times 10 to the 9th, 2.5 microcoulombs divided by 0.2 meters. What is the voltage that charge 1 creates at location X? What do you get? 112,500 volts. Now that's not the total voltage at location X. Isn't there another charge in the diagram? What's the magnitude of the second charge compared to the first charge? The same? What's the distance of the second charge from location X compared to the first charge? The same? So can you tell me what would the voltage of charge 2 at location X be if the magnitude of the charge is the same and the distance of the charge is the same? That's a nice, I did that on purpose, Courtney, just to cut down on the number of calculations. And I think if you see this in your workbook or in your homework, you'll notice they often give you identical charges because they're saying, if they were different, you could crunch the numbers. Let's just save you some time. So I think this then, the voltage at location X is going to be 112,500 times 2, right? Which is? Times 2 on your calculator with your current answer? You realize you could have just gone times 2 on your calculator with your current answer instead of retyping it? Huh? Did you not get the 112,500? But you have an answer button. I guarantee it. Or you could have done it in your head and come up with 225,000 volts. The voltage at location X, there is a total voltage of 225,000 volts. That means if you put a 5 Coulomb charge there, it would have 5 times that number joules of energy. And it would get repelled up, I'm pretty sure, if it was positive. Or if you put a negative 5 Coulomb charge there, it would have negative 5 times that energy. If you wanted to move it out to infinity where there was a charge of 0, you'd have negative energy. You'd have to add work. You'd have to do work. Emily, what does B want me to find? I don't know what you said. Where? Because I asked you to. Where? Why? Because I asked you. Welcome back. I missed you last day. Okay, so we're going to do the same thing. I'm going to find the voltage from location 1 at Y, which I think is just going to be still 9 times 10 to the 9th. Charge 1, 2.5 times 10 to the negative 6. Divided by, Emily, what's the distance between charge 1 and location Y? Thank you. This one I don't think is going to work out too evenly because 0.35 has a 7 in it, and 7 is not a nice number to do math with. Yeah, do you get 64,285.7? 64285.7? Yes? Anybody else? Okay. Oh, I should also find the voltage from charge 2 at Y. Oh, do I need to type it in? You mean it's, again, the same magnitude as charge 1 and the same distance as charge 1? So I'm just going to write same as V1, comma, Y. So the voltage at Y is going to be this number times 2. This number times 2. Cole, what I'm going to do is I'm going to go second function answer times 2, because that would be way faster than retyping everything, because my calculator has an answer button. No, it's actually voltage at Y, not Y's. Single Y. Get it? Y's? Someone will explain it to Rob. 128, so although normally I'd round off, I'm going to carry a few extra sig figs. 128,571. So to 3 sig figs, it would be 1.29 times 10 to the 5th volts, because the 8 would get rounded up. So there's my 3 sig figs, or 1.3 times 10 to the 5th volts. But I found the voltage at location A. I found the voltage at location X. I found the voltage at location Y. Are they the same? Is the answer to A and B the same? That must mean that depending on whether I'm moving a negative charge or a positive charge, it will either take work to move from location Y to location X, or I'll be able to let go of it at location Y and it'll fall down to location X. I'm not sure. Let's see. Oh, C says find the potential difference, the change in. Okay. That's going to be Vx minus Vy. Double check, is that final minus initial? Yeah, when I look at part D, it says to move from Y to X. So Y is initial and X is final. So I am going final minus initial. It's going to be 225,000 minus 128,571. Although what I'm going to do is I'm going to go 225,000 minus, I was clever enough to keep that answer on my calculator. So I get 96,428.57143. 96,428.6. Or if I went to 2 sig figs or 3 sig figs, 9.64 times 10 to the 4th volts. Kevin, what does D want me to find? Now, folks, put your pencils down and watch. I could do this. In fact, I will do that. You can write that part down if you want to. But then I could say, hey, what's changing anything? And you would say, so I could go, don't write this down, K, Q1, Q2, all over R final, which is location. Oops, that's wrong, Mr. Duick. That eraser didn't work. Let's try that again. Location X minus K, Q1, don't write this down, Q2 over location Y, which would be acceptable, but it would be repeating work, no pun intended, that I don't need to do, because I can also define work a different way. We already said this. potential energy is charge times voltage. Because we define voltage as energy divided by charge, so that must mean that energy is voltage times charge. With me okay, Alejandro? I think it's reasonable then to say this, because the charge that you're moving isn't changing. The voltage that it's traveling through is what's changing. In other words, I think I can say that this is just going to be Q change in voltage. Now, why is this so much shorter? How big is the charge that we're moving? What does it say in part D? Micro? Careful. Positive or negative, because I have to include the signs because it's a scalar. So, positive 1.25 times 10 to the negative 3 milli. How big is the potential difference that we're traveling through? That's what we figured out in part C. 96,428.6. Now, Cole, I would prefer not to round off, so I'm just going to go this number, which is still stored on my calculator, times 1.25 times 10 to the negative 3. So even though I wrote Q change in voltage, I went on my calculator, change in voltage times Q, since I happen to have the answer just sitting there. And I get 120.5 or 121 joules of work. What that is saying is, for me to move from here to here, I have to add energy. Well, of course I do, because it doesn't want to move towards these positives, so I would be adding energy up to right about there. But as soon as I got past halfway between them, now I can relax a little bit, because now it's getting repelled by those positives. Now it would want to go the rest of the way on its own. That would be a very difficult thing, Sebastian, for me to try and keep track of and calculate. Oh no, because it's a scalar, potential lets me take care of all of that automatically. Otherwise, I'd have to find hey, where is exactly halfway, find how much work it takes to get there, find out how much energy I gain. That'd be yucky. Or, what if it was a negative charge? If it was a negative charge, I'd have a negative answer. What that would be saying is it wants to fall down to about here. It wants to fall from here to about here, and then its momentum will keep it going for the way to there, and it still has some energy left. How much energy? You can probably find out how fast it's moving, because it would all be kinetic. So all sorts of little options, all sorts of openings appear. So I wrote here, if the charges begin and end at rest, then the work will just be the change in potential, which is the charge times the change in voltage. Example 5, I said, prove it. Nah, it's a pretty easy proof. In fact, I kind of already did with my little rant here, so I'm not going to bother. Instead, we're going to go to our summary. How can we find potential? Another word for which is voltage. You can find it from the point charge. Oh, sorry, hang on, this is the wrong definition. You can find it from the definition if you're told the potential energy of a test charge. Here's how we define voltage. We said it's how much energy per Coulomb. So if you put a charge somewhere and you know how much energy it has, divide those two numbers. That's the voltage at that location, the potential at that location. Sort of, Zach, how high you are. But no. You can also find it using the point charge equation if you know the big planetary charge that's causing the electric field, which is causing the voltage. You notice I used little q for the first one to show you a little tiny field charge at that location. Big Q for this is the planet causing the voltage. What about for energy? Well, we can find potential energy of a system in two ways. We can find it using the potential energy equation if we know both charges and their separation distance. Or we can find it using our definition of voltage by rearranging the voltage definition to get energy by itself. Oh, and the second one also, if I put a change in front of the potential and a change in front of the voltage, now I have change in potential energy, which is work if you're starting and ending at rest. Please notice potential energy and potential, or voltage, aren't vectors. They have no direction. They can be positive or negative, but that just tells you energy loss or energy gain. What that means is because they're scalars, we include the plus or minus signs of the charges. If they're both negative, put both negatives in, you'll end up with a positive voltage. One of each, you'll end up with a negative voltage. That means something. Okay. What's your homework? Here's what I assigned my block A's. You need to practice this, but you have lots of time. You got a full half hour. Number 1, 2, 3, 4, 5, 6, 7, 9, and 12. I'll say that again, now I'll do it on your guys's. 1, 2, 3, 4, 5, 6, 7. You can circle those, Graydon. 1, 2, 3, 4, 5, 6, 7, 9, and 12. Take a look at number 7, please. One, 2, 3, 4, 5, 6, 7, 9, and 12. Take a look at number 7, please. What's number 7 asking you to find? To solve this one, number 7, go KE initial plus PE initial equals KE final plus PE final. This is a job for energy. Why? Is there a change in speed? Yes. Is there a change in height? There's a change in voltage, which is sort of like height. See how I worked that in? Assume you're starting at rest, and we've just finished saying this is now QV equals a half m little v squared plus QV. This will be V final, voltage initial. This is the equation that has pairs of V's in it, 2 different V's. This is, Courtney, where I strongly suggest use the little wings on the capital V, or come up with some way that you can clearly tell that your V is a capital and that V for velocity or speed is a lowercase v. We're going to spend way more time on number 7 in the next few days, but I snuck one in here for you to think about. Little video to show you, and then I'll turn you loose.